Hello, welcome back. So by now you understand how this network that we built here works. And yeah, one feature is that unlike before, where we flattened the image right away, we now kept the two-dimensional shape of the image until the very end. And you can already intuitively understand that this makes it a lot easier to find some distinctive features in an image, because images are two-dimensional. So if you flatten them right away, you're losing all of the spatial information to recognize shapes and objects and so on. Whereas here we are keeping this two-dimensional feature of an image until the very end when we do the classification. But are we done yet? Can we train this network here and get a good result? Well, not quite. I'll have to show you two more features that make deep learning networks different from the classical networks. So again, we are going to add two new types of layers. Before we only had this dense layer, this fully connected layer. And one thing that people had problems with for a long time when they tried to apply backpropagation on these multi-layer networks is that, remember how it works, yeah? You compute the gradient of the loss function. And when you do this over multiple layers, the gradient is going to get smaller and smaller and smaller. So two things can basically happen depending on which direction you go on the gradient. It gets so small that you have a vanishing gradient. It essentially becomes zero because your precision is not enough to capture the very small value, or the weights go just in the opposite direction. They become too big and you have an overflow. Now they become not a number. And again, you cannot do a calculation on the weight. So this was a problem for a long time. People used a number of tricks on still being able to train these networks. But yeah, that was a big problem. They would train these networks. It might be okay for a while. You train it for hours and hours and hours, and the weights update. And then suddenly the network would basically explode. Now you have an overflow and all the training was for nothing because just aborts with an overflow error. So the technique that's used nowadays is inserting a special layer, which is called a batch normalization layer. So basically, we're going to add these normalization layers in there, and to avoid these values from becoming either too big or too small, they are going to be normalized at each step. So mathematically is done with the standard deviation of the input channel and then normalizing it. And it learns these additional two parameters and basically takes the input, normalizes it, and feeds it as the output. And by adding these normalization layers, we are actually able to apply the training algorithm over these large networks without the problems of numerical overflow or underflow. So that's the first new technique used in these deep learning networks. And the other type of layer that's new is a so-called dropout layer. So you've already seen on even the simple network that we did earlier that there is a lot of weights to learn. Remember, we had something like 600,000 parameters for the simple network from before, but we only had 50,000 training images. So for all of these parameters that we want to learn, we didn't really have enough training data. And what's happening in machine learning is it's going to overfit. It doesn't have enough samples to learn a good abstract representation, so it learns exactly what it needs to get the input data right. And the more layers, the more weights, the more parameters we add, the worse this is going to get, because even though we have now a lot more training data, the networks are becoming bigger and bigger and have more and more parameters. So again, there is a trick which is a special kind of layer, which is called a dropout layer. And what this layer will do is randomly will drop, meaning set the value to 0 from some of its inputs. So for example, here, it could decide that randomly it will not forward the value here, it will just set it to 0. And then in the next round, it will pick 2 others. So how many are being dropped is defined in the dropout rate. So here it's 50%. 4 inputs, it will drop 2 inputs at each step. And this basically forces the network to learn a representation that doesn't rely overly on any of the input features. So it forces the network to be a bit more abstract. This is only applied during training. So later when you are done, when you're finished training and you're using the model for testing, this dropout layer isn't doing anything. So then you're feeding the complete input. This is only applied during the training phase. So this helps us, our network, to learn a more abstract representation without overfitting to the training data. And now we can actually define our complete neural network. So again, we have the input layer. Then we have a 2D convolution operation. This is the same that we did before, but then afterwards we apply the normalization. Sorry, where was I? Yeah. We are using a special kind of redo here, leaky redo, which looks a little bit different. You can look at the link I had earlier to see how this looks like. Then we are adding 3 more convolution layers here with different sizes of kernel and strides. Finally, we have a flattened layer. Oh, sorry, and after each convolution, again, we are doing the normalization. Yeah, because at each step, we have to be sure that we don't have exploding or vanishing gradients. And then at the end, again, we have a flattened layer, a densely connected layer, another normalization. And here we also have the dropout layer. And then finally, the output layer with the softmax activation for 10 different classes. So now if you implement this and print out the network architecture again, you see the complete network that we have here. So I didn't fit everything onto the slide, but no, you get the idea. You can try it out yourself. So you have the input layer, 2D convolution, normalization, ReLU activation function, another 2D convolution, normalization, and so on. So at the end, for each layer, you see the number of parameters, the number of weights that you have to train. And now you can see we're already up to more than 500,000 weights that we have to learn. So for just 50,000 training samples, that's quite a lot of parameters. The actual training works just like before. It's the same optimizer, the same model, the same fit operation. And this is something that you can still train yourself. It's going to take a bit more time than the simple one we had before. But again, this is perfectly doable on a normal desktop or laptop in maybe 10, 15 minutes or so for the CFAR10 dataset. And now, if you evaluate this model, you can see that for a first improvement, we are already quite better than before. So we are up to an accuracy of 72%. And if we print out some examples, again, randomly selecting 10 images, looking at the network classification versus the real label, you can see it's quite a bit better. So here, frog correct, bird correct, automobile correct, deer is correct, airplane correct, the cat, again, a car. So the only 2 it got wrong here is the frog and this one here, which even for a human isn't that easy to see. It's a deer and not a horse. And last one, a cat. So for a first improvement, this is quite good. And you'll see some of the real world CNNs that are being used are using even more layers. Now we had something like 10 layers in total here, and there are networks with 20, 30, 40, 50 layers for image classification, for example. Okay, so much for CNNs for images. And in the next part, I'll tell you how we can use the same idea for processing natural language text. See you then.